Good morning, everybody. Today we will continue with phase changes and heat transfer in materials. The phases or states of matter are solid, liquid, and gas. You already know this information from your high school years. But in addition to these three main phases, there is an additional phase which is called as plasma. But I will not go into detail with the plasma. Today we will discuss the phase changes between solid and liquid, liquid and solid, or liquid and gas, okay? We will discuss these phase changes. What is this phase change? A phase change is a transition from one phase to another, from solid to liquid, from liquid to gas, or from gas to liquid, from liquid to solid. This is the phase change. And during the phase change, the temperature does not change. Okay, this is important. So we will discuss this one. Of course, during this phase change, you have to transfer a heat to the system. And a heat transfer in a phase change is given with this equation here, with Q is equal to M times L. M here is the mass of material that changes phase, and L is latent heat for this phase change. So the latent heat L is the heat per unit mass that is transferred in a phase change. Here you see an example. Let's consider here we have a glass of water on the right side, okay, and in addition to the water we have ice cubes, okay. You see many ice cubes here within the water, and we have a thermometer here, okay, digital thermometer, and what do you see here? 0 degrees Celsius. The surrounding air is at room temperature. So here we have temperature around 300 Kelvin or 27 degrees Celsius, okay? But the temperature within this cup or within this glass is 0 degrees Celsius, okay? Why? Until all of the ice has melted and the phase change is complete, we have this temperature, okay? So during the phase change, the temperature does not change. So these ice cubes have melted, okay? And from solid to liquid, their phase will change, okay? And during this phase change, temperature does not change. It stays at 0 degrees Celsius, okay? So, of course, during this phase change, you have to give a heat to the system. If you are adding heat, then it is given with plus. If you are taking heat from the system, it is given with negative sign. So here we have a graph related to the temperature versus time. This is the temperature axis here in degrees Celsius, and here we have time axis, and here we have minus 25 degrees Celsius, here we have 0 degrees Celsius, here we have 100 degrees Celsius. This is the phase graph for the water, okay? Here, between A and B on the left side, we have ice, okay? And we add heat to the system, and the temperature of the ice increases, okay? Then ice warms, okay? There is no phase change here. We add this heat to the system, which is given with mc delta T. We change the temperature of the ice material. And between B and C here, within this graph, within B and C, we add heat by time, okay? And this heat is given with this expression, Q is equal to M times L, okay? But temperature of the material does not change, okay? Here in this part of the graph, ice melts to liquid water at 0 degrees Celsius. We add heat to the system, which is given with Q is equal to M times L, but temperature does not change, okay? Only phase changes here. So in this part between A and B, we have liquid phase, and between B and C, from solid to liquid, we change the phase. And from C to D, in this part, we add additional heat to the system, again, which is given with MC delta T. Okay, I'm talking about this one. So we increase the temperature of the water. We increase the temperature of the liquid here. There is no phase change here. We just increase the temperature of the system. So then liquid water warms, okay? And here between D and E, the temperature is constant, 100 degrees Celsius, and we add this heat to the system, which is given with M times L, and between D and E, liquid water vaporizes to steam at 100 degrees Celsius. So here between D and E, we have phase change, okay? Temperature does not change here, but the phase changes. And here, point E, we have vapor, okay? And then you can also increase the temperature of the vapor, okay? So this is the boiling water, and you increase the temperature of the vapor of water. So then steam warms in this part, and you have to add this heat to the system in order to increase the temperature of the steam. Is it clear? Is there any question in this part? So between here, between B and C, phase changes. Between D and E, phase changes. And during this phase changes, the temperature is fixed, temperature is constant, temperature does not change. Okay, so here we have talked about Q minus plus L, okay? This is called as heat of fusion, or as we have defined here, latent heat, okay? So you can see these names. And here there is a metal gallium. Why it is liquid here? Because its melting temperature is 29.8 degrees Celsius, and it has heat of fusion or latent heat, which is given with 8.04 times 10 to 4 joule per kilogram. So it has relatively low melting temperature compared to the other metals. For example, if you compare with iron, if you compare with cobalt, they have huge melting temperatures, around 1000 degrees Celsius. So, but this metal gallium has very low melting temperature, and at room temperature, it can be melted. And what about the heat of vaporization? Here you see 3 children, and they play in the swimming pool. Just consider that water is warm and air conditions are also very good, let's say. Just consider a hot day. But when these children step out of the swimming pool, they will feel cold. Why? Because there is water on the surface of these children. There is water, okay? So when they step out of the swimming pool, this water evaporates from their skin and it removes the heat of vaporization from their bodies. It's this one. Okay. On the surface of the children, there is a water, and in order to vaporize, this water will take this heat from their bodies, and then they will feel cold. So here we have heat of fusion and heat of vaporization for some materials. Here we have helium. This is the normal melting point in Kelvin and degrees Celsius on the left side. Here we have heat of fusion in joule per kilogram. And here we have normal boiling point in Kelvin again and degrees Celsius. And here we have heat of vaporization. Okay, this heat of fusion, this is the heat of vaporization, LV. So what about helium for boiling point? During the last lecture, I have explained the boiling point of helium is 4.2 Kelvin, about minus 269 degrees Celsius. Okay, it is very cold liquid. And here there is a hydrogen, and it has also boiling point 20 Kelvin and minus 252 degrees Celsius. Here there is an oxygen. Okay, it boils at 90 Kelvin. So this is the transition temperature from solid to the liquid, and this is the transition temperature from liquid to the vapor. Okay, and this is very important for space applications, space shuttles to carry persons or payload to the space. Liquid oxygen is used as a fuel. Okay, so it has very low boiling point. And what do you see here? There is a mercury and water here, you already know, and sulfur, lead, antimony, silver, gold, copper. Look at the copper. What about the boiling point? Melting temperature is this one, melting point 1356 Kelvin, okay, or 1083 degrees Celsius, and boiling point is this one for the copper. So this information is very important when you are designing something in industry, okay, or when you are dealing with some biological or chemical substances. You have to use special equipment, special material for intended temperatures. Let me continue with this example. Example 17.7 from the book, a temperature change with no phase change. A camper pours 0.3 kilogram of coffee initially in a pot at 70 degrees Celsius onto a 0.12 kilogram aluminum cup initially at 20 degrees Celsius. What is the equilibrium temperature? Assume that coffee has the same specific heat as water and that no heat is exchanged with surroundings. So what is the meaning of this one? This is usually found in the questions, okay, important term. This defines isolation or insulation, okay? So here, let's say there is a pot and there is a coffee in, okay? It is hot and the temperature is 70 degrees Celsius. And here you have a cup, okay? And you will put this coffee into this cup, and this cup has initial temperature of 20 degrees Celsius. So question is that, what is the equilibrium temperature? Very easy question. So in order to go to the thermal equilibrium, this will give heat to this system. So this pot will give heat to this cup on the right side, and this cup will take heat from the pot, okay? This is the mechanism, but the heat taken by the cup is equal to the heat given by the pot, okay? So you can consider like this. This is the heat given by the coffee. This is the heat taken by the aluminum. And you can also write this one like this. The heat given by the coffee plus the heat taken by the aluminum. In total, they are equal to 0, okay? So this is the positive you give to the right side to the aluminum cup, and this is the negative you take from the coffee to the aluminum cup. So then we have this relation. There is no phase change here. Then we have this relation. This is the delta Tc, temperature change of the coffee, and this is the specific heat of the water. Why we use specific heat of the water? Because here in the question it is assumed that coffee has the same specific heat as water, but this is assumption. And this is mass of the coffee, it is given. This is mass of the aluminum cup. This is specific heat of the aluminum. And here we have change in the temperature of the aluminum cup. And then if you reorganize this expression, then you can get the final temperature or equilibrium temperature, which is given 66 degrees Celsius. Do you have any question here? Then let me continue with the example 17.8, changes in both temperature and phase. Here, temperature changes, okay? So this is the final temperature of the coffee and final temperature of the aluminum cup, but there is no phase change. In this question, we have changes in both temperature and phase. What is the question? A glass contains 0.25 kilogram of Omni Cola, mostly water, initially at 25 degrees Celsius. Here we have, let's say, 0.25 kilogram Omni Cola within this glass. How much ice initially at minus 20 degrees Celsius must you add to obtain a final temperature of 0 degrees Celsius with all the ice melted? Ignore the heat capacity of the glass. So this Omni Cola at the beginning has this temperature, 25 degrees Celsius, and we have ice cubes here, and they have initial temperature of minus 20 degrees Celsius. And you will take this ice cubes, you will put them into the cola, and the final temperature of the system will be 0 degrees Celsius, okay? But what we have here, we have liquid cola, and here we have solid ice, okay? And this solid ice will be melted. They will go from solid to the liquid. So here we have phase change, okay? So then we have to use this equation. Here we have Q1 and Q2. This is the Q1. This ice cubes will take heat from the cola, okay? Then their temperature will increase. It is given with this expression M1 C1 delta T1, okay? And here we have Q2. So the phase diagram for this ice cubes is like this. Here we have time, and here we have temperature, okay? Initial temperature of the ice cubes is 20 degrees Celsius, and they will go to 0, okay? And they will be melted, okay? So here we have Q1, and here we have Q2. Q2 is phase change. It is written with M times L. Okay, then we have all heat expressions here within this equation. In total, they will be equal to 0. And here, let me also write down the temperature change of this cola here on the left side. This is the time. At the beginning, the temperature is 25 degrees Celsius, and by time its temperature will go to the 0. Okay, but there is no phase change here. It will be liquid at 0 degrees Celsius. Okay, so we have just here QMC delta T. But here we have both Q on the right side with the ice cube. We have QMC delta T and we have QML. And just put all the numbers here, then you can calculate the required ice cube mass in order to have this final 0 degrees Celsius in the Omni-Cola. I have two more examples with this part. Example 17.9, what is cooking? A hot copper pot of mass 2 kg, including its copper lid, is at a temperature of 150 degrees Celsius. We have a copper pot and it has certain lid. Let's say this is the lid of the copper pot and its initial temperature is 150 degrees Celsius. You pour 0.1 kilogram of cool water at 25 degrees Celsius into the pot. So you open the lid and then you put water, okay, into this hot pot, but the initial temperature of the water is 25 degrees Celsius. Okay, then quickly replace the lid so no steam can escape. So you can imagine the initial temperature of this cup is 150 degrees Celsius. If you put water, some part of the water will vaporize, okay? So then, in order to keep the vapor of the water within the copper pot, you quickly close the lid. Find the final temperature of the pot and its contents and determine the phase of the water, liquid, gas, or a mixture. Assume that no heat is lost to the surroundings. Again, you consider that this system is isolated from the surrounding, from the environment, okay? So what is the question? What is the final temperature of the system? And also, what is the final phase of the water? This is the question. And we have three possible conditions. The first one, no water boils, and the final temperature, T, is less than 100 degrees Celsius. So you put this water into this hot copper pot and you increase the temperature of the water, but the temperature is less than 100 degrees Celsius. This is the first condition. The second condition, some water boils, giving a mixture of water and steam at 100 degrees Celsius. So these are the possibilities. And the last one is all the water boils and vaporize, giving 0.1 kilogram of steam at 100 degrees Celsius or with greater temperature. Okay, just discuss these three conditions, these three possible conditions. So if you consider that no water boils and the final temperature is less than 100 degrees Celsius, so then you can write this expression. Water was liquid at the beginning, and here again it is liquid, but its temperature increases, okay? Then here we have Q water. Water takes heat from the copper pot, and plus here we have copper pot gives heat to the water, okay? And in total it is equal to 0. So this is MC delta T for the water. This is the MC delta T for the copper pot, okay? And if you solve this one, So here we have specific heat of copper, specific heat of water, okay, and mass of copper pot, initial temperature of water, initial temperature of copper pot, and mass of water. So if you use all the things in the equation above, then we will have this expression. Okay, so this is the final temperature of the system. If you consider that no water boils and the final temperature is less than 100 degrees Celsius. So what is the final temperature? If you follow this way, final temperature is 106 degrees Celsius. So then this first condition is not valid, okay? Just have a look at the second condition. Let me use another color. This is the second possibility. Some water boils, giving a mixture of water and steam at 100 degrees Celsius. Just use this expression. So in this case, what we have? In this case, we have this one, Q mc delta T for the water, and ml for the water, and mc delta T for the copper pot. What do you see here? The temperature of all of the water should go from 25 degrees Celsius to 100 degrees Celsius, okay? And this expression gives this one. All the water goes from 25 degrees Celsius to the 100 degrees Celsius, and some part of the water after this 100 degrees Celsius, some part of the water evaporates. We have phase change from the liquid to the vapor to the steam. And what we see here, X times M water, only small portion of the water evaporates. So this is the second possibility we are discussing now, okay? The second condition. Then if you take this X from this expression, you will get this type of relation. And then X will be 0.034, okay? So 0.034% of the mass will be vaporized, okay? What about the initial mass of the water? The initial mass of the water is 0.1 kilogram, and only this portion of the water is vaporized. Then 3.4 gram of water is converted to steam at 100 degrees Celsius. This is the solution. Do you have any question here? Okay, the last one. Example 17.10, combustion, temperature change and phase change. In a particular camp stove, only 30% of the energy released in burning gasoline goes to the heating the water in a pot on the stove. How much gasoline must be burned to heat 1 liter or 1 kilogram of water from 20 degrees Celsius to 100 degrees Celsius and boil away 0.25 kilogram of it? So here you have a camp stove, and there is a gasoline within this one, and you use this gasoline, and here there is the water, okay? So, but the important thing here is that only 30% of the energy released in burning gasoline goes to the heating the water in a pot on the stove. So we have 1 kilogram of water, and we would like to increase its temperature from 20 degrees Celsius to 100 degrees Celsius, and we would like to boil away 0.25 kilogram of the water. So then, in order to increase the temperature of the water from 20 degrees Celsius to 100 degrees Celsius, we need this one. First of all, just draw the diagram, phase diagram in degrees Celsius. Okay, at the beginning, what is the temperature of the water? It is 20 degrees Celsius, and it will increase up to 100 degrees Celsius. Okay, and some portion of it will be boiled away. So for this part, I write this one Q1 mc delta T, and I calculate it, this one here, 1 kilogram water, and this is the specific heat of water, and this is the delta T, change in the temperature from 20 degrees Celsius to the 100 degrees Celsius. Then the Q1 is this one in Joule. And to boil 0.25 kilogram of water at 100 degrees Celsius, it is given here, mass is given, and here we have Q2 in this part. Only 0.25 kilogram of water will be boiled. Okay, then this is the mass, this is the LV for the water from the table, and it requires this heat, 5.64 times 10 to 5 joule. Okay, then the total energy needed is Q1 plus Q2, 8.99 times 10 to 5 joule. Okay, and this is 30% of the total heat of combustion. Here, this is the heat source. This heat is given by the camp stove. Okay, we use gasoline, but only 30% of the gasoline gives us energy to heat the water. Others are not used for heating. Okay, so the total energy is needed with Q1 plus Q2. Okay, in order to have this condition of water here in this level, and this is the 30% of the total heat of combustion. Then you can calculate the gasoline you need to burn to heat 1 liter of water from this 20 degrees Celsius to 100 degrees Celsius. The combustion of 1 gram of gasoline releases this 46,000 joule. Okay, then in order to produce this energy, this heat, we need 65 gram gasoline. Okay, or 0.9 liter of gasoline. And after this point, I would like to continue with the mechanisms of heat transfer. We have 3 mechanisms of heat transfer. One is conduction here, and the second one is convection, and the third one is radiation. We will investigate 3 of them. And here we have a general information. In nature, energy naturally flows from higher temperature objects to lower temperature objects. This is called heat transfer or heat flow. Okay, so here you see object with high temperature, and here there is another object with low temperature, and let's consider you have contact in between, and heat is transferred from high temperature object to the low temperature object. Okay, so we will discuss what is conduction, what is convection, what is radiation. Conduction occurs within a body or between 2 bodies in contact. Okay, here you have a body with some certain temperature T1, and here you have another body with temperature T2. Okay, and then if they have different temperatures, there will be heat transfer in between, okay, from high temperature to the low temperature. And what is the convection? Convection depends on motion of mass from one region of space to another. This happens in fluids or gases, okay? Just consider winds, hot winds or cold winds. Just consider the heating system of the houses, okay? So convection is used. I will go into detail a little bit. And then the last one is the radiation. Radiation is heat transfer by electromagnetic radiation. So in the conduction, this one, And also in convection, you need a medium, you need a material. But in case of radiation, you don't need any medium, okay? Heat transfer can be done without any medium by electromagnetic radiation, electromagnetic waves. For example, sunshine, electromagnetic waves, electromagnetic radiation comes from the sun and transfer heat to the earth, okay? With no need for matter to be present in the space between bodies, okay? So this is the main difference of the radiation, heat transfer by radiation. So let me continue with the conduction of heat. In conduction, heat flows from higher to a lower temperature, as we have discussed. Just consider here we have an object on the left side, this object on the left side with higher temperature. And on the right side, we have another object with lower temperature. Okay, let's say this is cold, this is hot. And in between, we have a thermally conducting material. Okay, thermally conducting material. And it has certain cross-sectional area A. It has certain length. Okay, then the heat will be transferred from the hot object to the cold object, okay? So you transfer heat. Heat is this one, Q, okay? So the rate of heat flow is given as this one. So by time, heat changes, you transfer heat, and heat current, heat flow in conduction is given with this one. Heat flow or heat current. This is the rate of heat flow, dq over dt, and it is given with K times A. This is the temperatures of hot and cold ends of rod, temperature of this left side. This is the temperature of the right side, cold part. And this is the length of the rod. This is the area, cross-sectional area of the rod. And this is the thermal conductivity of rod material, K here. So which kind of material you have to use for good thermal conductivity? Usually metals are good thermal conductors. In addition to that, metals are good electrical conductors because they have free electrons, okay? But this is the usual case. Of course, from one metal to another metal, this thermal conductivity changes. I will also discuss this one on a table. So now look at this equation. Here we have area and here we have length. We have discussed this one in the previous transparency, heat current H from the hot object to the cold object. And here in figure B, we have two rods with same cross section and same length, okay? What about the heat current? So length is same. Look at the equation here. Length is same, but what about the area? Area is increased. I have one area here, another area here. In this case, we have just single area here. Okay, so since this area is doubled, then this heat current in conduction will also be doubled if you keep everything constant here in the equation. And look at the C figure here. In this part, area is same, but I have used a longer rod, okay? Then look at the equation. Ka, temperature of the hot object minus temperature of the cold object, L. Area is fixed, K is constant, and this part is fixed. Then I increase this one. If I increase the length of the rod, then the heat current will be decreased. Okay, so this is the relation between area and length of the thermal conductor in heat current. So here we have some thermal conductivities of common substances. For example, here we have silver. It has 406 watt per meter per Kelvin. Here we have copper, here we have aluminum. These are the metals. You see, of course, conductivity of silver is much better compared to the aluminum. And here we have wood. Wood has very low thermal conductivity, you see. And here there is a concrete. It also has very low thermal conductivity compared to the metals. Just compare. Here there's a fiberglass. It also has very low thermal conductivity. And this is styrofoam, which is usually used in the thermal isolation of the buildings, okay? It also has very low thermal conductivity, okay? The lowest value here in this table. Look at the bio application, fur versus blubber. This is the fur of fox, and this is the whale, bowhead whale, okay? The fur of an Arctic fox is a good thermal insulator because it traps air which has a low thermal conductivity K. The value K 0.0 watt per meter per Kelvin for fur is higher than for air. So what do you see here? The thermal conductivity of air, this one. This is the thermal conductivity of air, 0.024 watt per meter per Kelvin, okay? Air is not good thermal conductor, okay? And what about the thermal conductivity of fur of this fox, this one? So what is the information here? The fur of the fox traps air. So within the fur of this fox, air is trapped, okay? So due to the air within this fur, this fox has very low thermal conductivity, okay? So the thermal conductivity is this one, 0.04 watt per meter per Kelvin, okay? Because it contains air within the fur. So then let's consider the outside temperature is minus 20 degrees Celsius and inside temperature of this body is, let's say, I don't know actually, but just consider 38 degrees Celsius. So due to the fur, there is a good thermal insulation. And look at the veil here, the layer of fat beneath a bowhead whale skin. So there is a fat. So this is the body of the whale, let's say. Okay, and just beneath the skin, there is an insulating layer, this one. This insulating layer is fat. Another name is blubber, balık yağı, okay? And this has this thermal conductivity. What do you see here? 0.24 watt per meter per Kelvin. Okay, this is the thermal conductivity of this fat here. Look at the thermal conductivity of the fur for the fox. The thermal conductivity of the fur is this one. And this is the thermal conductivity of the blubber fat. So a 6 centimeter thickness of blubber is required to give the same insulation as 1 centimeter fur. So just consider that here we have, with the thickness of 1 centimeter, we have a fur, and in order to provide the same insulation, you need 6 centimeter of fat. Okay, so this fur is much better thermal insulation material. And there is a information here. Just let me remind you, there is a term which is used in industry, in civil engineering, also in other applications of the science and engineering, thermal resistance. Here, within this equation, we have K, right? Thermal conductivity. And here we have length, thickness, okay? Length of the rod or thickness of the fat, thickness of the fur, let's say. So if you take this L over K, this gives us the thermal resistance. So in order to have good thermal insulation, you have to have this low thermal conductivity. Okay, so if you have low thermal conductivity, then you will have high thermal resistance. Okay, then even very small thickness will be enough to thermally insulate the system from environmental conditions. Do you have any question here in this part? Okay, then let me continue with this example. Example 17.11, conduction into a picnic cooler. A styrofoam cooler has total wall area, including lid, of 0.8 meters square, and wall thickness is 2 centimeters. It is filled with ice, water, and cans of Omni Cola, all at 0 degrees Celsius. What is the rate of heat flow into the cooler if the temperature of outside wall is 30 degrees Celsius? How much ice melts in 3 hours? This is the question. So we have this cap. It is made from styrofoam, okay? It has certain thickness, 2 centimeters, and we have water, ice cubes, and also cola within this one, and it also has a lid. Okay, lid also made from styrofoam with the same thickness. Okay, then you can save your cola cold for a long time within this cooler. So, but what about the outside temperature? Outside temperature is 30 degrees Celsius and inside temperature is 0 degrees Celsius. So there will be heat flow from outside to the inside, okay? Then what about the question? What is the heat rate of heat flow into the cooler? Heat rate is given with this one. This is the K. You can find it from the table for the styrofoam. Look at the styrofoam. It is 0.027 watt per meter per Kelvin for the styrofoam. And then just use it here. And the area is given, okay? If you consider this area, you can calculate heat flow, the rate of heat flow into the cooler. And then here we have temperature change from 30 degrees Celsius to the 0 degrees Celsius. And this is the L. What is L? Thickness of this styrofoam, okay? This thickness is 2 centimeters, 0.02 meter. Then you can find 32.4 watts or 32.4 joule per second. Okay, why joule per second? Because it is given with dq per dt. This H, we have done it in the previous transparencies. Q is given in joule and T is given in second. Okay, H is given in watt. So then what about the second question? How much ice melts in 3 hours? We have ice cubes, okay, within this cooler, and within 3 hours, how much ice melts? So the total heat flow within 3 hours can be written by this expression. Just look at this equation, dq over dt. And from this expression, you can get this one. Q is equal to H times T. We have calculated H and time is given in the question, 3 hours, 10,800 seconds, okay? Then heat of fusion of ice is given, okay? Then just use this equation, Q is equal to mLF. Q is found here, just use this Q, and then LF must be given in the question. Then 1 kilogram ice will be melted in 3 hours. This is the answer of the question. Let me continue with the example 17.12, convection through 2 bars. Here we have steel, okay, and steel has length of 10 centimeter, and here we have copper, and copper has length of 20 centimeter, okay. So a steel bar 10 centimeter long is welded end to end to a copper bar 20 centimeter long. Each bar has a square cross section, so 2 centimeter on a side. The free end of the steel bar is kept at 100 degrees Celsius by placing it in contact with steam. So here we have steam on the left side, and this part of the steel is 100 degrees Celsius. And free end of the copper bar is kept at 0 degrees Celsius by placing it in contact with ice, and on the right side there is ice touches to the copper, and temperature is 0 degrees Celsius. Both bars are perfectly insulated on their sides. So you consider that there is no contact with the surroundings or with the environment, then system is thermally isolated. Find the steady state temperature at the junction of the 2 bars and the total rate of heat flow through the bars. What is the final temperature at the junction here? What is the junction? Junction is this one, this part. Okay, this is the junction. So what is the final temperature of this junction? And what is the total rate of heat flow through the bars? So there will be heat flow from this side to this side, okay? And also from this side to this side, from the hot side to the cold side. So now we have HS here, we have H copper here. So this is the heat flow from steel to the copper. So we have hot and cold temperatures, 100 degrees Celsius and 0 degrees Celsius. Okay, then just calculate this HS, which is given with thermal conductivity of the steel, cross-sectional area, and the temperature change. We don't know the final temperature. This is the length of steel, and this is equal to the heat flow for the copper. This is thermal conductivity of the copper, cross-sectional area of the copper. This is the final temperature of the junction minus initial temperature of the copper and length of the copper. So if you solve this equation, then you can get expression for the final temperature. So if you put all information into this equation, finally we can find this T, 20.7 degrees Celsius. This was the first part of the question. What is the temperature of the junction? Okay. And the second part of the question, what is the total rate of heat flow? Total rate of heat flow, HS plus H copper. We know the T here, we know the T here. If you use them here, then finally you can calculate this one. In total, we will have HS plus H copper. Okay, do you have any question here? Let me continue with the second condition with the same example, conduction through 2 bars 2. Suppose 2 bars of example 17.12 are separated. One end of each bar is capped at 100 degrees Celsius and the other end of each bar is capped at 0 degrees Celsius, what is the total heat current in 2 bars? Okay, again, total heat current HS plus H copper is asked, but now the situation is a bit different. Again, this side is 100 degrees Celsius and right side is 0 degrees Celsius. Here we have 20 centimeter long copper and here we have 10 centimeter long steel. Then just calculate. So here we have higher temperature minus lower temperature. Higher temperature is 100 degrees Celsius, lower temperature is 0 degrees Celsius, so delta T is 100 Kelvin. So you can use it here for both steel and copper. And finally, you can calculate this one. Okay, any question here? So let me continue with the convection of heat. As I explained at the beginning of this part, convection is the transfer of heat by mass motion of fluid. Here we have a metal rod, and then this part is very hot, let's say, okay, and then you transfer heat to this water here, and this hot water, this hot liquid flows in the fluid, okay? So then we transfer the heat by mass motion of fluid. So this fluid transfer the heat to the other parts of the fluid, okay? So this one, a heating element in the tip of this submerged tube warms the surrounding water, producing a complex pattern of free convection. So this is convection. You can also consider house heating systems. Just consider this is a house, okay, and here you have heating element, okay, and this heat is transferred to the other parts of the house by air, okay, by flow of air. This is the convection. So you are sitting here and you don't have any thermal connection, but this heat produced by this heater is transferred to this guy by convection, okay, by air. And let me continue with the radiation of heat. Radiation is the transfer of heat by electromagnetic waves, such as visible light or infrared. Other electromagnetic waves, X-rays, gamma rays can also transfer heat by radiation, and sunshine also transfer heat from the sun to the earth, okay? And this has many applications. And here you see a picture taken by the infrared camera. Infrared cameras are usually used for military applications. So you see this is a cold beverage, okay, cola or cold water, let's say. And this is the body of human. This is cloth, okay, and this is the skin of the body, you see, and cold part emits different electromagnetic waves and hot parts emit different electromagnetic waves. So then infrared photograph reveals radiation emitted by various parts of the human body. And strongest emission comes from the warmest areas, while there is very little emission from the bottle of cold beverage. So then what about the heat current? So heat, let's say there is a guy here, and here there is an infrared camera, and heat comes from this guy to this camera, and from different parts of the guy. So different heat comes to the active area of the camera. Then this heat current in radiation is given with this expression. A times E times sigma times T power 4 A is the area of emitting surface, and E is emissivity of surface. Okay, this a specific value for each surface. And here we have Stefan Boltzmann constant. The sigma here is constant. And here we have absolute temperature of surface. So let's consider the temperature of this cold beverage is, let's say, 10 degrees Celsius. And the temperature of the skin is, let's say, 26 degrees Celsius. And temperature of this cloth here, 27 degrees Celsius. Okay, so each surface has different temperature, okay, and different surface area. Then there will be a different heat current in radiation. Do you have any question here in this part? So I have 2 examples and 1 more transparency. Then I will finish my lecture. Example 17.14, heat transfer by radiation. A thin square steel plate, 10 centimeter on a side, is heated in a blacksmith's forge to 800 degrees Celsius. If the emissivity is 0.6, what is the total rate of radiation of energy from the plate? So this is asked. Area is given. You can calculate from this one. This is the area. Emissivity is given. And sigma is the constant, Stefan Boltzmann constant. And what about the temperature? Temperature is 800 degrees Celsius. Be careful. You have to convert this one to the Kelvin. Okay. Then just put it there. And then the result is 900 watts. And radiation from human body. What is the total rate of radiation of energy from a human body with surface area of 1.2 meters square and the surface temperature of 30 degrees Celsius or 303 Kelvin if the surroundings are at a temperature of 20 degrees Celsius? What is the net rate of radiative heat loss from the body? The emissivity of human body is very close to unity, irrespective of skin pigmentation. So this is the body radiation at a rate, okay? So area of the body, emissivity is 1, Stefan Boltzmann constant, and this is the temperature of the body, power 4. Then this is the total rate of radiation of energy, this one, which we have calculated. And then this loss is partly offset by absorption of radiation, which depends on the temperature of the surroundings. The net rate of radiative energy transfer. So this is the temperature of the body, and this is the temperature of the surrounding, okay? This is given with 293 Kelvin, but in the question is 20 degrees Celsius. And this is 303 Kelvin, temperature of the body. It is actually 30 degrees in Celsius, okay? So then we have net rate of radiative energy transfer, which is given with this expression, okay? Just put all the numbers here, then we have this expression. So body is losing heat. Any question with these examples? This is the last transparency, radiation and climate change. So just consider that this is the Earth, okay? So, and it has some certain mean temperature, okay? Then it will radiate. The heat will be transferred from Earth to the space, okay? But there is an atmosphere around the Earth, okay? And in the atmosphere, there are many particles, okay? And this radiation will be back reflected, okay? radiation comes from the Earth, but it will be reflected by the particles here. What kind of particles? We have nitrogen, we have hydrogen, we have carbon dioxide, okay? And also we have dust particles, okay? Many particles and molecules within the atmosphere. So then this radiation will be reflected by these particles, okay? But if you increase the dust particles, if you increase the amount of carbon dioxide in the atmosphere, this radiation will be reflected more compared to the previous case, okay? Then the Earth will be hot, okay? So the overall temperature of the Earth, okay, will increase. Then this will result in a global warming and dangerous for the life in the Earth. So you see here a graph. On the left side, we have difference in global average temperature from 1951 to 1980, okay? And here in this scale, we have years from 1880 to 2000. What do you see here? The average temperature of Earth increases, okay? You see here, maybe you can say that it is very small increase, okay? Let's say 0.6 degrees Celsius, very small increase, but actually it matters, okay? It results very bad situations. So this is the relation between radiation and climate change, okay? If the atmosphere here around the Earth contains less dust particles and less carbon dioxide, then this heat will be transferred by radiation to the space, okay? Then we can keep the Earth's temperature more or less constant without increasing, okay? But what about the source of this carbon dioxide molecules? Where does it come from? It comes from the industry, okay? Increased atmospheric carbon dioxide due to the burning of fossil fuels is the cause of this continuing increase in global average temperatures. Do you have any question here? With this one, I have finished my lecture. Take care of yourself. Bye-bye.